Welcome to Complex Analysis Lesson 10 on Analytic Functions. We'll first talk about a definition for an analytic function and then follow up with several properties that analytic functions have. A complex function is analytic. Sometimes the term holomorphic is used at a point z sub 0 if it has a derivative at each point in some neighborhood of z sub 0. So we have a counterexample that we looked at before, although we didn't use the term analytic at the time. But if you have f of z equals the modulus of z squared, we showed that it only had a derivative at z equals 0. From the definition of analytic, it's not analytic anywhere, because not even at z equals 0, because any neighborhood about z equals 0 has points, all the points actually except for z equals 0, where the derivative does not exist. We also have something called a singularity. For example, f of z equals 1 over z minus 1 plus I. This function does not have a derivative where at 1 plus I, it blows up there. But anywhere as close as you want to get to 1 plus I, you do have a derivative. So that's called a singularity. It will come up a lot when we talk about contour integrals in series, where the singularities are actually important points to look at when evaluating series and integrals. In some cases we need to avoid them actually, but that doesn't mean they aren't important. Okay, and then one last definition here. An entire complex function is one that's analytic over the entire complex plane. Well, in this slide, we're going to define some topological concepts. In neighborhood, open disk, sometimes open ball is used, is basically the set of points about a point z sub 0 of a given radius, in this case delta. So writing it out here, the open ball about z sub 0, or neighborhood, it is all points of distance less than delta, strictly less than delta, from a given point z sub 0. The little dotted line here means the boundary is not included, and that's because we had a strictly less than here. If you take a point, a set y, say this squiggly set here, and a point is called interior to y if we can draw a neighborhood about it that's completely within y. So we see here z has a neighborhood about it of radius delta, which is completely within y. A set that contains only interior points, or should I say a set all of whose points are interior, is called open. So if we don't have the boundary of y here, that's missing, not included, then this y would be an open set. So we can get as close as we want to the boundary, and we can still draw a small neighborhood about that point that's completely in y. If we included the boundary of y, then it would no longer be open, because at any point on the boundary, it would be impossible to draw a neighborhood about that point that's completely within the set. Now we have a little bit more general definition of neighborhood, which we're not going to use as far as I can recall in the future lessons, but I thought I'd just give it here for completeness. So we have a subset y, for example, maybe our set here y, of a topological space X, and in our case that'll be the complex plane, is a neighborhood of a point X if there is an open set U such that X is in U and U is a subset of Y. So the wrinkle here is that your set Y is a neighborhood if you can find an open set that a neighborhood of Z, I should say, if you can find an open set that includes Z that's completely within Y. So we could have Y including its boundary, in which case it would be closed set, or even if it had part of its boundary and then some of it was not included, it would be neither open nor closed. But because there's a neighborhood within Y that completely is in Y and contains Z, then we would say Y is a neighborhood of Z based on this definition here. But as I say, we're not going to use that definition as far as I recall. It's the more general definition given in topology. Now, we have another concept called connected, and it's pretty much what you would think. On the left, we have two different connected sets. This one on the top is connected. You can see from any point, you can draw a line to another point in the set. Even if you put a hole in it, you still have a connected set. For example, if you have a point here and another point here, you can draw a line, curved line, totally within the set and between the 2 points. There's no 2 points that you can pick in this set where you can't connect them with a curved line or a straight line in some cases. Okay, so these are connected. In fact, they're open connected sets, and that'll be an important condition for a number of the theorems that come in later lectures. Open connected. Now, I should show you an example of not connected. So if we take these two circles together, these, you can take a point in here and a point in here, and there's no way of getting between the 2 points without leaving the set. So this is not a connected set. On this slide and the next, we're going to state some properties of analytic functions. The first property is similar to what we had for derivatives. If the sum, differences, product, and composition of analytic functions are analytic, and the quotient of two analytic functions is also analytic, assuming the denominator does not equal 0 at any point. As a byproduct of the second sentence, we also have the reciprocal of an analytic function that isn't 0 anywhere, and it is also analytic. If an analytic function is invertible and has a derivative which is nowhere 0, then its inverse is also analytic. This one's rather interesting. Every analytic function is smooth in the sense of having infinitely many derivatives. So you can take the first, second, third, fourth, and so on derivative, and they should all exist. In some cases, they might be 0, but they all exist. And this comes from something we haven't gotten to yet. It's the something called the Cauchy integral formula, or an extension to it, and it's a way of using this integral to define derivatives of a function. And I put it here, but it may not make a lot of sense to you until we actually get into contour integrals. So we'll just put that here for your future reference. We will get back to this eventually, but we don't have the tools yet to prove this theorem. Okay, we have a few more properties on this slide. Liouville's theorem, an entire function that's bounded must be constant. So just writing it out more formally here, if the modulus of f of z is less than some constant m over the entire complex plane, then the function is bounded, and by this property it must be a constant. Equivalently, if you have a non-constant function over the entire complex plane, then it has an unbounded range. So there must be points where it either goes off to plus or minus infinity, which is a bit surprising. There's a Wikipedia article on Liouville's theorem. It proves the theorem actually, but it uses contour integrals and complex series in two topics which we'll get to later, but so far we haven't talked about these at all. If f of z is analytic over a domain, an open connected set, and if the derivative equals 0 everywhere in that domain, then f is constant. There's a proof of that in section 24 of the book by Brown and Churchill, which I referenced in the introduction to this series of lectures. So you may want to, if you're really interested in proofs, you may want to get a copy of Brown and Churchill. An analytic function over a domain is uniquely determined over the domain by its values in a subdomain S, so some subdomain of D, or along even a line segment. So that's also a bit surprising that just by looking at some subdomain of a domain or a line segment in the domain, that you completely determine all the values of the analytic function in that domain. And that's again related to contour integrals. We'll talk about that later.